In this video, we're going to continue looking at hypothesis testing. We're going to pick up right where the last video left off. In that video, we had just gone over the first step of hypothesis testing, which was stating your hypotheses. All right, now we're on to the second step, specify the significance level. So, first off, what is the significance level and why is it important? All right, the significance level of a test is the probability of making a type 1 error. Alright, so the probability of making a type 1 error. And we've actually dealt with the significance level already because we could write this out as we have, right? Significance level is the probability of making a type 1 error. Alright, but we can also write that out mathematically. Right, the probability of making a type 1 error equals alpha. Right, we've already dealt with alpha when we were developing our confidence intervals, right? So alpha is the significance level. And once again, it's the probability of making a type 1 error. All right, so what is a type 1 error? Right, a type 1 error is when we reject the null hypothesis when the null hypothesis is true. All right, so we haven't gotten to the conclusion section yet, and we won't for a little while. But when we get to that, we'll see that we have two conclusions for our hypothesis test. Right? The first is reject the null hypothesis and conclude that the alternative is true. And the other potential outcome is that we fail to reject the null hypothesis. All right, so with a type 1 error, we're rejecting the null hypothesis. We're saying the null hypothesis is false. However, it's actually true, right? So that's why we've made an error, right? So if we were looking at this in terms of our criminal trial analogy that we've been using, right, a type 1 error would be when we convict an innocent person, all right? So looking at it in that perspective, right, we can understand why we want to keep alpha low, which is what we want to do, right? We want to minimize alpha as much as is reasonable, right? If we think about our different confidence levels, right, and the alphas, we can kind of put those in context of this, right? So a 90% confidence level has a alpha of 0.1, right, or 10% significance level. Right, so 10% of the time, right, or the probability of 0.1, we could make a type 1 error, right? For 95%, that's a 5% significance level. So there is a probability of 0.05 that we make a type 1 error, right? 99%, there is a 0.01 probability of making a type 1 error. All right, so some of those probably not sufficient. Actually, depending on who you ask, all of those might not be sufficient for the criminal case aspect, right? So kind of think for 90%, 1 out of every 10 people sentenced to or convicted of a crime didn't do it. The 95%, 1 in 20, 99%, 1 in 100, right? Those aren't really great things. So that's probably not sufficient for a criminal case. But for what we're doing, right, we're going to pick the one that's best, right, that's most suited, right, or really what we're going to do is we're going to look at all three of them and compare in the real world. We're not going to do that as much in this class, but in the real world you would do your test and then you would compare the different kind of significance levels. But regardless, all right, the ultimate thing here is that significance level tells us the probability of making a type 1 error. We want to minimize the risk of making a type 1 error, right? And we're going to stick to those confidence levels that we've already been using, those three standard ones. Now, if we have type 1 errors, that would indicate that there are also other types of errors, and that is correct. There's one other type of error that we're going to talk about. All right, and that is a type 2 error. So a type 2 error is when we fail to reject the null hypothesis. When our alternative hypothesis is true. All right, so again, kind of using the concept of the trial, right? A type 2 error there would be so failing to reject the null hypothesis, right? So we're saying we can't prove that they're not guilty, right? We can't prove that they're guilty, so we're just gonna have to keep going with that for now, right? But they actually are guilty. All right, so again, so in other words, letting a guilty person walk free. All right, so just like in our just like in our judicial system, right, the probability of making a type 1 error is inversely related to the probability of making a type 2 error. Right, so as we decrease the probability of making a type 1 error, right, we increase the probability of making a type 2 error. Right. Also, just like in our justice system, or at least the way it should be, we would prefer to minimize the risk of a type 1 error at the expense of increasing the probability of a type 2 error. Right. Type 2 error also has, it's called the power of the test, or not, excuse me. Right. The probability of making a type 2 error is known as beta, right, or symbolized as beta, and it is called the power of the test. We're not going to really worry about that. There's some information on that in your book if you are interested, but again, our focus is more on those type 1 errors. That's what we really want to avoid, so that's what we're going to focus on. All right, to just further kind of illustrate this, sometimes it's helpful to draw out a little chart. All right, I can already tell that's not going to be big enough. Let's see if we can do that again. All right, that's close enough. All right, so for our columns, this first one, this is where H naught is true, right? The null hypothesis is true in these two cells, right? In these two cells, the alternative hypothesis is true. So this is a statement of fact. Which one's true? Right, over here, right, the rows are going to be our decision or our conclusion. right? So the top row is where we reject the null hypothesis. The bottom row is where we fail to reject the null hypothesis. So if we reject the null hypothesis when the null hypothesis is true, that is when we're going to make a type 1 error. If we reject the null hypothesis when the alternative is true, we haven't made an error. That's the correct decision, right? If the alternative is true, we want to reject the null hypothesis, right? If we fail to reject the null hypothesis when the null hypothesis is true, that's also a correct decision, right? So null hypothesis is true, so why would we want to reject it? Right, and then finally, right, if we fail to reject the null hypothesis when the alternative is true, this is when we would make a type 2 error. All right, so in regards to this section, most of the time we're not actually in this class, we're not going to be specifying this significance level, or at least you're not. And the reason for that is because I'm going to just specify it for you. I'm going to tell you to conduct your hypothesis test at the 95% level, or you know, the 95% confidence level, or the 5% significance level. You know, there are numerous ways that I could signify what that is, right? But most of the time I'm going to specify that for you. You're not going to have to do it yourself. Again, in the real world, we wouldn't just pick one of those 3 commonly used ones and compare it. We would check all 3, but that's because in the real world you'd be doing this with computers, right? So we're just going to stick with just kind of picking one and examining it, all right? But again, we're not going to really be specifying that significance level much in this class, but it is important to know what that significance level means, right? Knowing what a type 2 error is, right? Or type 1 error, type 2 error, knowing both of those and knowing kind of how to spot those. All right. On to the next step, all right? The next step is to determine the critical value. So determining the critical value. All right, so critical value shouldn't sound unfamiliar, right? We've already dealt with critical values in the last chapter when we were working with our confidence intervals, right? So those are our kind of Z's and T's that we get from the chart, right? Right now we're going to just focus on the Z distribution, all right? But we'll get to that in just a second. All right, so the critical value is used to determine our conclusion, right? It's one of the main things that we're going to use to make our decision about whether we reject or fail to reject the null hypothesis, right? If we're looking at it in this analogy of a criminal case, right, we can kind of think of the critical value as the burden of proof, how much evidence we need to present to the jury for them to reject the null hypothesis and accept the alternative hypothesis. All right, so the higher that critical value, the higher that number, the more evidence we need to have. All right, so now let's, so that's kind of just the basics. They're gonna work more or less exactly as we have seen them with some small differences. But let's go ahead and look at the critical values, or how we find the critical values for our different tests. All right, so just like with our confidence intervals, right, the significance level, or alpha, is going to determine what our critical values are, right? So whatever significance level, or by proxy confidence level, whatever level we're doing the test at, that is going to determine what our critical value should be. All right, once we find that, we're going to, it's going to define what we call the rejection region. All All right, so let's start by looking at our two-tailed critical value and kind of looking at those rejection regions and talking more about what we mean by that. All right, so for two-tailed test, our critical value should be pretty familiar, right? It's gonna look familiar. It's Z alpha divided by 2, all right? So if we're at the 5% significance level, right, that's 0.05 for alpha, divide that by 2 is 0.025, right? And we would go get that critical value off of one of our charts. All right, an important thing to note with two-tailed tests is that when we're doing a two-tailed test, we do not have one critical value. We actually have 2, right? Because we're splitting that into kind of, well, let's just draw this up here. All right, so let's say that this is our distribution, right? So for our critical values, right, what they do is they define the rejection region. Okay, so just as a preview, right? So what these rejection regions are is they're kind of defining the areas in which if we, the next thing that we look at, which is the test statistic, right? If the test statistic falls into these rejection regions, we reject the null hypothesis, all right? Essentially what it's telling us is that if we land in these, right, it's very unlikely that the null hypothesis is true, right? We'll get into that in a little bit as well, right? The area under the curve in these rejection regions equals alpha, right? So individually, they equal alpha divided by 2 in the case of a two-tailed test, right? The reason for this is because we don't care if, when we're doing a two-tailed test, we don't care if our mean is far above, far greater than that arbitrary constant or far lower than that arbitrary constant. Either way, we want to know. So that's why we have 2 rejection regions and why we split that, that alpha between the 2 tails. And this is also why they're called two-tailed tests, right? Because there's 2 tails, right? There's 2 rejection regions, 1 in each of the tails, right? So that is what those critical values are going to look like. Just to make this, hopefully make this a little bit clearer, let's actually define, let's say for this, we're going to do kind of a 95% confidence level. So our Z, all right, Z alpha divided by 2, which would be Z 0.0250. You don't really need that 0. All right, this would be 1.96. All right, so this means that we would have a positive 1.96 that defines the rejection region in the right tail, and a negative 1.96 that defines the rejection region in the left tail. All right. So really, that was just a long walk to get to the point where I'm saying you'll get your single value, right, and then you've got a positive 1 and a negative 1, and you have 2 critical values defining a rejection region in both tails of the distribution. All Right? A lot of this stuff kind of builds on top of each other, so it'll make more sense once we start doing some examples. But that is that rejection region. Really, the main takeaway is how to find that critical value. If you're doing a two-tailed test, you need to find the z alpha divided by 2. Right? And again, before we do these other ones, just so we know, there are a couple of ways that we can find these critical values. One, we could take that z 0.025. Right? Once we know that that is a number where the probability that z is less than that number is equal to 0.025. So we could go to our standard normal chart, look in the middle, look for that probability, go out to the edge, find negative 1.96, right? And know that that's our critical value. Or what is arguably much easier, we could go to our t-distribution. Right, we could find that 0.025 along the top, right? It'll be like t subscript 0.025. Go all the way down to the bottom of that chart where we have that infinite degrees of freedom row, and there you will see 1.96 telling you that that's the critical value as well, right? Remember, we can do this because the t-distribution becomes the z-distribution as n goes to infinity. So if you're looking at the infinite degrees of freedom, you are looking at the critical values for the z-distribution, all right? That's by far gonna be the easiest way to find these. All right, so now that we've got that taken care of, let's move on to the other types of tests and how we find their critical values. All right, so for our right-tailed and left-tailed test, you're gonna find the critical value the exact same way. It's just you're gonna have to make sure you make some modifications as needed, and we'll see what we mean by that. All right, so for both right and left-tailed tests, what we want to look for is z alpha. All right, so this is a bit of a change up from what we have been doing with our confidence intervals and our two-tailed test. All right, but with our one-tailed test, we are only going to have a rejection region in one tail. So we're not needing to cut alpha up, right? It's all going to get put into one place, all right? So it's just alpha. Now, the difference is that your right-tailed test, your critical value should be positive. For a left-tailed test, it's going to be negative, right? So just want to make that distinction because I'm going to notate them exactly the same. I'm just going to notate it as z alpha, and we'll just have to remember to make those negative or positive as is necessary. Now, one way to help us remember to do this is to draw out the distributions, all right? I'm gonna continue drawing these out, especially once we get into the example phase. The reason for that is because for anyone who's more visual, it can help remind you of, say you're doing a right-tailed test, you get your critical value, you say, well, I don't remember if it's positive or negative. Well, if you know it's a right-tailed test, right, that means that the rejection region has to be in the right tail, right? So the critical value has to be positive. All right, same idea is true for our left-tailed tests. All right, if we forget to make, the more common thing that's gonna happen is that you're gonna do a left-tailed test and you're gonna forget to make it negative. And so again, drawing out the distribution can remind you to say, oh, this is to the left of 0, this needs to be negative, right? If you got 1.645, that's not to the, that should be to the right of 0. So this must be negative 1.645 or whatever your critical value turns out to be. All right, there's some other reasons we're going to continue drawing these up, but we'll get into that as we need to. But those are our critical values, right? And again, they're going to be found just like we were finding them for the other stuff. All right, so just like we were finding them for the two-tailed and the critical value, or the confidence intervals. All right, it's going to be done exactly the same way. I think that is it. Yep. So again, if you're doing a 95%, then Z 0.05, that's going to be 1.645. If you're doing a 99%, you don't split alpha in half, it's still 0.01. So you're going to get 2.326 or something along those lines. All right, again, you don't need to memorize these. If you do it a bunch, you'll eventually start memorizing them, and for years if you do it. But using that t-distribution chart is by far the easiest way to find those. All right, so we're going to go ahead and stop here. In the next video, we're going to look at one of my favorite parts of this, which is calculating the test statistic. All right, you're probably not going to like it, but I'm going to have a lot of fun with it. So you can look forward to that, and then we'll probably finish up all of our steps in that next video, and then the one after that will be examples. All right, but that's it for this video. I will see you next time.